Hello everybody, and welcome to the Module 10 video for Introduction to Logic. In this module, we will be learning about Boolean schemata. And you might wonder, so this is a new type of schemata, and you might wonder why we need it. So if you remember, in the end of the chapter on term logic, I hinted that there were sentences like, if all pies are delicious, then someone eats every pie. Okay, and so if we look at this, this mixes truth functional operators, so we have an if-then there, with things that look a lot like our term logic sentences. And there are certain arguments where for the premises to imply the conclusion, we have to pay attention or find some way of representing the structure of sentences like these. So what we'll be doing for the rest of the course, basically, is we will be learning different techniques for testing schemata that can represent both the categorical relations that are in term logic and the truth functional relations that we've been learning about in the first half of the course. And we'll be able to test those sentences for validity, consistency, and inconsistency. Okay? And you'll see probably in a few chapters just how powerful this is, and this is sort of what makes logic, I don't know about useful, but this is a much more powerful logical system than the one that we have been learning up to this point. So all that you have to do in this chapter, the only thing you have to do in this module, is you have to learn to recognize the difference between three different types of Boolean schemata. You have Boolean term schemata, Boolean existence schemata, and Boolean statement schemata. And the reason why you have to learn to recognize the difference between these types of schemata is that if you can do that, then the validity tests for Boolean schemata in the next chapter will be incredibly easy. If you can convert stuff into conjunctive normal form and you can recognize the difference between these types of schemata, then you'll be able to follow the exactly precise instructions for applying that validity test that'll always tell you what step you need to do next. Please make sure that you have a good, clear grasp on these definitions before moving on. Before I go and explain the definitions and give you a bunch of examples of each of these types of Boolean schemata, I'm going to do a little bit of review, just basic stuff, validity, consistency, inconsistency, just to refresh you. Right? Okay, so moving on to review. Okay, I'm just going to go through the definitions of some key terms real quick because they'll be important for this chapter, more so the next one, but I wanted to remind you now. So remember, a schema is valid if it always comes out true. A schema is consistent if it's true at least once or comes out true at least once under at least one assignment of truth values or under one interpretation. And a schema is inconsistent if it never comes out true. Okay? And remember, you just had to do a chapter on this, but in case you forgot in the last week, a schema is in CNF or conjunctive normal form when it's a conjunction of clauses a conjunction of one or more clauses where each clause is an alternation of one or more single letters or negated single letters. Oops. Okay, and so if you are confused about that, any of these things, please go back. This is the right time to go back and review. Homework solutions for everything up through chapter 7, I believe, have been posted. I will get the chapter 8 solutions up sometime early this week, so please go back and check. If you know what all this stuff means and you can convert into conjunctive normal form, the next chapter is going to be easy. If you can't, it's going to be very hard. Okay, so let's move on to our different types of Boolean schemata. Okay, Boolean term schemata. I guess, so I don't have to write that out every time, I'm going to abbreviate this as BTS. Okay, so if you look here, this is a Boolean term schema. So let's break it down into see what's going on here. So how this works is, just like in term logic last chapter, the capital letters stand for terms. Okay? And they're the same sort of terms that you ran into when you were doing your Venn diagrams. So, if we wanted to put an English term word in for this letter P here, we could do, pies, right? Or pi. So again, these are terms. Terms refer to adjectives or nouns that indicate groups or sets or categories of things. So things like pies or pastries or anything that there can be a set of is a term. Okay? Right, pretty straightforward. The new thing that we have here, these x's are variables. And a variable stands in for an object. And an object, so if terms represent groups of things, right? Objects represent specific things. That's not a technical definition, but right. So we could, how do I want to say this? Frequently, and especially when we're dealing with Boolean schemata, we're not going to put in, we're not usually going to say which object we're talking about. We're really just more concerned about validity, consistency, inconsistency, and for that we don't need to know what English sentence our schema corresponds to. But if we wanted to read, let's put X or Quine in for X, right? Because there's only one Willard Van Orman Quine. He's a specific thing. And so if we plug in these things, what sentence A would say is that Quine is a pie, or Quine is not a pie. That is how we would translate this Boolean term schema A into English. For reasons that I do not think it would be helpful to explain right now, I just introduced this object X, but we're going to get rid of it. So we would simplify something like A to, let's call this A prime. P or not P. So another way of thinking about what a Boolean term schema is a Boolean term schema is exactly like every truth functional schema that you've seen up until this point in the class, except it has capital letters instead of lowercase letters. That is the only difference. I know it might be hard to tell here, but these have to be capital P's. So if you see something that looks exactly like the normal truth functional schemata that you have seen before in the class, except it has capital letters, you know that you have a Boolean term schema. And as you might suspect, given that this looks exactly like our good old-fashioned truth functional schemata, all of the same validity rules apply. So we can test these Boolean term schemata for validity, consistency, inconsistency using truth value analysis. If you've been paying really close attention, that might seem strange to you. And one of the reasons it might seem strange to you is because in the last chapter I said that terms aren't true or false. So they're true or false of an object, right? But the way that these work is Boolean term schemata is always going to have the same object in there. And because a term must either be true or false of some object, even if it can't be true or false on its own, right? Like if you just scream pies, that's not true. No, that's not a statement. That's not the sort of thing that can be true or false. But if you were to say, Quine is a pie, that's the sort of thing that can be true or false. So you can think of it as we're just putting in an X here for any object, we don't know what, and then we're kind of abbreviating it away. And that's why these things, Boolean term schemata, we can do truth value analysis the same way. I'm not going to give you examples of this. It's exactly like truth value analysis, except with capital letters. So I'm just going to give you some more examples of this. And so actually, one thing to note about A, the Boolean term schemata in A, if you probably recognize by now that if we were to do a truth value analysis, I'll just do one, P or not P, false, true. So this is a valid Boolean term schema by truth value analysis. And because it's valid, any valid Boolean term schema, it doesn't matter what object we put in for X there. It'll always come out true of that object, right? So remember, this says that X is a pie or X is not a pie. And it's true of pies that they're pies or not pies. They're pies. It's true of you that you're a pie or you're not a pie. You're not a pie, right? If you destroyed kind of everything in the universe except, like, I don't know, 3 pancakes, it would be true of them that they're pies or not pies because they're not pies. Okay? So Boolean term schemata, pretty straightforward. Okay, so I'm just going to work through a few more examples of Boolean term schemata, or work through. I'm just going to show you a few examples. Again, these are exactly like our good old-fashioned truth functional schemata. The only difference is they have capital letters. So, P and and not P, that's a Boolean term schema. I'm just making things up. So if we have, that's a Boolean term schema. Oh, that's a really ugly E. I don't know why I did that. No parentheses. That's a Boolean term schema. That's a Boolean term schema. Okay? Yeah. And so, again, these work exactly like our truth functional schemata. We can do truth value analysis on them to find out whether or not they're valid, consistent, or inconsistent. Pretty simple, pretty straightforward. It's all there really is to know about Boolean term schemata. Again, just remember, associate this term, Boolean term schemata, with things that look exactly like our truth functional schemata, except they have capital letters instead of lowercase letters. Okay? Pretty straightforward. Let's move on to Boolean existence schemata. Okay. The next type of schema that we need to learn to identify and recognize is known as a Boolean existence schemata, or they are known as Boolean existence schemata, which I'm going to abbreviate as BES. Get off my iPad. Okay, sorry, my cat was attacking my iPad. Okay, and so how these work is, how these work, so this is a Boolean existence schema, and how it works is we have this backwards E, and Quine doesn't actually call it a quantifier at this point, but I'm just going to call it an existential quantifier. And how we read this, this means there exists and okay. So the definition of a Boolean existence schemata, or of Boolean existence schemata, is a Boolean existence schema is this backwards E, an existential quantifier, followed by a Boolean term schema. Okay, and so if we put in for the term P, X is a pi, and if we put in for the term D here in our schema, X is delicious. Remember, we're abbreviating away the X. We would read this sentence right here as some pies are delicious, or there exist delicious pies. Okay. Again, pretty straightforward. It's just a backwards E followed by a Boolean term schema. So capital letters instead of lowercase letters. And again, this sum here, I said this in the terminology video, but just to emphasize, sum means at least one. If we say there exists, that means there's at least one. Okay? This actually, well, I'm out of space. I'll erase some stuff. So this, the first example, Boolean existence schema that we have, this says the same thing as a type I sentence would in term logic, right? And we can actually, I'm not going to go through the translations right now, but we can actually rewrite every single one of our sentence forms in term logic with a Boolean existence schema. Okay, so let's look at some more examples of this just so that you can see them. So example B, let's do existential quantifier P, G, S, or not S. Okay, so and we're going to use P for X is a pie, D for X is delicious. I'm just going to do S, X is sweet. And so if we translate S like that, we would read this as some delicious pies are not sweet. Or that's the good English anyway. Perhaps a more literal way of rendering this would be there exists something, or at least one thing, that is a pie and delicious and not sweet. And this right here is something that we could not represent directly in term logic, right? Just a few more examples of these and how they would be translated. Let's see. I'm not going to make you translate these, by the way. I'm just so you understand what the symbols mean is why I'm doing this. They're really awkward. We have a better way of representing these directly. Okay, so if we have this sentence right here, this example C, what this says is that some sweet and delicious things are not pies. Or, I mean, again, more literally, again, the most literal translation, based on the fact that it's a conjunction here, is probably there exists something that is sweet and delicious and not a pie. Again, these are kind of messy for doing translations. I'm just trying to get you to understand what they mean, how to understand the backwards E. Okay, so another example. SGP. And again, these are from the book, so if you want to follow along with the reading. So the next example, and here we would translate this as, again, I'm just going to go with the most literal one. There exists something that is not sweet, delicious, and not a pie. Or maybe a little better, some non-sweet, delicious things are not pies. We have reached the point, though, where you get some of these, you will get some of these sentences that if you try to make them into a pleasant sounding English sentence, you're going to want to smash your head into a wall. Okay. So, yeah. So, how does validity work for these? For Boolean existence schemata? Well, so a Boolean existence schema is valid if and only if its term schema is valid right. Again, I'm not going to go too much into detail about why that's the case, but it is. Just trust me. It'll make sense once we get to the method of existential conditionals, I hope. Okay. So consistency and inconsistency work the same way. right? Again, nothing surprising here. Just to remind you, so like in this example, this is the term schema. The term schema is just what you get when you get rid of the backwards E. You get the term schema. It's the capital letters and the truth functions. So I'm going to give you just some examples so that you can recognize this of some valid, consistent, inconsistent Boolean existence schemata. So so if we had something like right, so you should be able to recognize by now at a glance that the terms inside of this, the term schema inside of this Boolean existence schema is valid. If you don't believe me, you can check just the term schema with truth value analysis. Oh, oops. Okay. So again, we can have stuff like, and these are perfectly fine Boolean existence schemata. We can have if we can have anything inside of a Boolean existence schemata as its term schema, so long as how do I want to say this? Anything that looks like any of the schemata that we've seen up until this point, except they have capital letters, can be the term schema of a Boolean existence schema. Okay, so both of these are valid, and they're valid because the term schema inside of them, P or not P, or if P then P, is valid. And again, you can convince yourself of that with a truth value analysis if you don't believe me. So some consistent Boolean existence schemata. Things like, this, right? Because again, P is, consistent, right? Something like this. Oh, I keep wanting to do the lowercase letters. I'm so used to it by now. Okay. Some examples of inconsistent Boolean existence schemata. So and again, you can just check the term schema via truth value analysis if you don't believe me. Right. So again, this is not too complicated. It's just this backwards E, which you read as there exists, followed by a Boolean term schema. And again, a Boolean term schema is just what we get if we take the sort of truth functional schemata we've been learning in the first 5 weeks of this class and replace the lowercase letters with capital letters. Okay? So one thing I have to warn you about, because I made this mistake a bunch when I was first taking this class. So this, is not right. So this is not a Boolean existence schema. No, bad, right? And the reason why it's not is because of this negation sign here. So remember, the definition, did I write it down? Yeah. So remember, the definition of a Boolean existence schema is we have a backwards E followed by a Boolean term schema. And so if we look at something like this, this is not a backwards E followed by a Boolean term schema. This is a negation sign followed by a backwards E followed by a Boolean term schema. And so, and this is important. This is very important. I'm not stressing this just to be pedantic. You will screw up the method of existential conditionals if you do not appreciate this fact. So I'm hammering it home. is that if you have a negation sign in front of a Boolean, if you have a negation sign in front of a Boolean existence schema, it is not a Boolean existence schema. It's the next kind. And again, just remember that this is not a Boolean existence schema. In order to have a Boolean existence schema, you have to have, this is fine. Right. So remember, the definition of a Boolean existence schema is backwards E followed by a Boolean term schema. Again, a Boolean term schema is just the sort of schema that we've been looking at throughout this class up until this point, just with capital letters instead of lowercase letters. And so we've definitely been looking at things like the negation of this alternation. And so this is fine. Just remember, if there's a negation sign in front of the backwards E, it is not a Boolean existence schema. I cannot say that enough. I almost just want to sit here and repeat that for 10 minutes, but I'm not going to out of respect for you. But please remember that fact. Okay, so next, going to move on to Boolean statement schemata. Okay, the last sort of Boolean schema that we have to learn about is a Boolean statement, or they are known as Boolean statement schemata. Okay? Excuse me. Sorry. So I'm just going to give you a few examples before I give you the definition. So, and again, these are from the book. Okay. So the definition that Quine gives, and this is an adequate definition if you understand how to interpret it, is that Boolean statement schemata are truth functions of Boolean existence schemata. Okay. Most of you are probably like, what? And that's that's understandable. I struggled with this, understanding what this meant myself the first time that I took this class. And so I guess more intuitively, maybe a better definition is a BSS, or a Boolean statement schemata, is what you get if you replace all the letters in a truth functional schemata, or truth functional schema, with Boolean existence schemata. Okay, again, that probably still confuses you a little bit, but let me show you what I mean with these examples up here. Okay, so let me move some of this around. So let's look at A first. So if we were to, so consider the schema not P, right? So if we were to replace the P with a Boolean existence schema, and remember, a Boolean existence schema is just a backwards E followed by a Boolean term schema. So if we were to replace in our, this is a lowercase p by the way, in our good old-fashioned truth functional schemata, let's say that we're going to replace this P here with the Boolean existence schema, this. right? And so just to remind you, this is a Boolean existence schema, a BES, and it's a Boolean existence schema because it is a backwards E followed by a Boolean term schema. And again, a Boolean term schema is just a good old-fashioned truth functional schema, but with capital letters. So if we were to replace in this truth functional schema not P, if we were to replace the P with this over here, this Boolean existence schema, we would get this, right? Yeah, again, I'll just show you what I mean with all these examples. It's not the end of the world if this confuses you a little bit, as long as you can recognize them. Okay, so for the second one, right, this, so it's a conditional. So if we had the truth functional schema, not P therefore Q, and we replace P with this Boolean existence schema and Q with this Boolean existence schema, right, we would get this. Right, so to say that Boolean statement schemata are truth functions of Boolean existence schemata just means that it's like we took one of our good old-fashioned truth functional schemata and we replaced all of the letters with Boolean existence schemata. So again here, let me move this again. 1 second. Okay, so here, right, let me do it below just so you can see. So right, so here these two sentences have the same like outward logical structure, and if we started from this truth functional one and we replaced P with this Boolean existence schema, Q with this Boolean existence schema, and R with this Boolean existence schema, we'd get this Boolean statement schema, right? So that's what they are. I'm actually not going to bother trying to translate these. I looked at the examples I picked in the book and I was like, whoa, it's really hard to read things like, especially like V and C in English. We'll get to another system for representing that in a way that more closely matches English in a little bit, in a week or two, right? So learn how to recognize these. So remember, if you have a negation sign in front of a backwards E anywhere, it has to be a Boolean statement schema, right? Similarly, if you have things that are connected with truth functions like this, the whole thing has to be a Boolean statement schema. Definitely, if you have negation signs in front of backwards E's and truth functional operators, it has to be a Boolean statement schema, right? And remember, Boolean statement schemata are made up of truth functions, so logical operators combined with Boolean existence schemata. And Boolean existence schemata are just a backwards E followed by a normal truth functional schemata, just with capital letters instead of lowercase letters. So there's not that much more that you need to know about these other than recognizing them, but there's one kind of law you need to know, or rule, I guess, and that it doesn't have a name. It's that the backwards E distributes over alternation. And what that means is that, say we have something like this, this is equivalent to similarly, if we had something like Right, this is equivalent to, oops. And it also goes the other way around. So if we have E, right, this is equivalent to, okay. But you have to, so this is pretty straightforward. However, you need to pay attention because the backwards E does not distribute over conjunction. Right, and so so this is wrong. Right, don't do this. Doesn't distribute over conjunction. And also, if you have a negation sign in front of it, that doesn't distribute either. So oops. Okay, so you can't do what I'm doing right here. This is an example of something that's wrong. Right. Okay. Cool. So no, bad. Don't do that. Okay. So those are the two restrictions. You'll have to know this for the next chapter, but it'll be kind of clear. So all you have to do for the exercises is tell me which kind of, I give you a bunch of examples, and this is going to be the same way it is on the quiz, is tell me whether it's a Boolean term schema, a Boolean existence schema, or a Boolean statement schema. That's about all you need to know right now. The utility or usefulness of all of this will become clear when we move into the next chapter of the method of existential conditionals. So good luck. This stuff really isn't that bad if you just go slow and look at the examples and definitions. I think you'll be able to figure it out. Okay.